Hi everyone, we are Group 17, and the members of the group are Zhi Yuanyao, Yi Junjia, and Jialin Gu. Today we will talk about security in mobile application. We divided our presentation into 5 parts. The part 1, how mobile applications work. Most mobile applications have client-server architecture. The client is the application installed on the mobile devices. These applications are usually downloaded from application distribution platforms. The server is usually a cluster of computers. It interacts with clients through data transmission channel and is responsible for processing and storing information. Comprehensive security checks of a mobile application include a search for vulnerability in the client and server, as well as data transmission between them. In this presentation, we will mainly focus on the security mechanism of a mobile operating system on which the mobile application runs. Currently, there are 2 main operating systems, Android and iOS. Next, I will introduce their security mechanism and compare them. Regarding Android's security mechanism, we mention the following 2 points here: the sandbox and the intent. The sandbox. Every application under Android is sandboxed into its own process and file system space. Taking advantage of the Linux kernel's process space protection mechanism, Android assigns each installed application a unique user ID. This allows the kernel to keep applications confined in memory, restrict access to underlying hardware or services, and restrict access to the file system on the device. By default, each application's data and resource are contained in the location which only the application and the core framework can access. The intent is the message object used to request operation from other components, regardless of whether the component is current application or another application. It's divided into 2 types, explicit and implicit. The workflow of the intent is that we assume that there is an activity A that needs to start an activity B. If started by the explicit intent, the system will start the component immediately. When using implicit intents, the Android system compares the contents of the intent with the intent filters to find the corresponding components to be launched. If the intent matches the intent filter, the system will start the component and pass the intent object to it. If multiple intent filters are compatible, the system will display a dialog box that allows the user to select the application to use. In order to ensure the security of the application, when using the implicit intent, we need to add security detection logic. Regarding to iOS security mechanism, we mention the following 2 points here. They are the security model and the iMessage security. The system security model is central to security in iOS. It makes the hardware and software securely integrated with each other such that every component in iOS is secure. 4 important parts need to be mentioned, namely secure boot chain, system software authorization server, and secure enclave touch ID security. The secure boot chain feature is that the bootloader starts to verify the signature for each step of the boot. If it fails, it will go to the recovery mode. The system's software authorization server is a remote server to prevent downgrade, and there is a mechanism called nonce used to prevent an attacker from saving the server's response and using it to tamper with the device or otherwise alter the system software. The secure enclave is a coordinated processor soldered in the chip. Its tasks mainly include key management, handling cryptographic operations, and keeping data integrity. Touch ID is a fingerprint sensor that can read fingerprints from users. Users who pass fingerprint verification can safely access some services provided by the devices. The iMessage is a very popular message communication service provided by Apple. iMessage extensively uses Apple push notification services, which is responsible for sending information to iOS and OS X devices in a secure way. When iMessage is turned on, an RSA key for encryption and an ECDSA key for signed are generated. The private keys for those two keys are stored in the device keychain. The public keys are sent to Apple Directory Service, which is responsible for storing user identification, his or her associated public keys, and devices' APNS addresses. Now let's compare the secure mechanism between Android and iOS. For Android, each application has its own sandbox directory and the permission is per application. It required the user to set the security for each application during install time. However, for iOS, all applications share a same sandbox model, which is defined by Apple, since it only allows users to access the system file in the root and the setting of the phone, not in each application. And iMessage is only contained by iOS. In addition to the differences mentioned above, Android and iOS have some other differences. Due to time reason, I will only briefly introduce them. For memory randomization, iOS apply it earlier than Android. In addition, iOS has code signing technology, so it makes iOS more secured. For encryption, Android uses disk encryption, while iOS introduced hardware encryption. Remote wipe by removing the encryption key for the device. Once the hardware key is removed, the device is useless for iOS operating system mobile devices. So Apple iOS device is more secured. In addition, for data storage format, for Android, the data can be stored in either built-in storage or external storage, while in iOS, the device itself don't have an external storage. For building antivirus part, Android user can give permission to download some applications from untrusted website, while iOS users can only download applications from the Apple Store. Therefore, the iOS operating system is more secured. In this presentation, we introduced the workflow of mobile applications, Android and iOS security mechanism, and compare the difference. We hope to help everyone better understanding security of the mobile application. These are references of our presentation. Thanks for listening.